All right, Zoom, can you hear me now? Okay, sorry about that. I had the mic turned off. All right, so okay, so I'll repeat. I went through a few announcements just now. So let me just repeat. So I think the main thing I wanted you guys to think about is your final project groups. And so yeah, I've had one group kind of reach out to me already. But make sure that you guys are kind of thinking about what kind of topics that you want to study. Think about your groups. And so another thing I said is that if you're having trouble, you know, if you're having trouble finding a group or you need help kind of finding a group of 3 or 4, just send me an email and then I can kind of put you guys together with other people looking for a group as well, right? But ideally, I'd like to have groups of 3 or 4, and you know, and you want to make sure that you form your groups, you know, ideally by the end of next week, so you can kind of start researching, because you know, the presentations are going to take place in week 16, and you want to make sure you have, you know, a good enough lead time to do the research and put the presentation together before then. Okay. So the topic that we're covering today is human motion kinematics, and so let me just remind you kind of what that is. Okay. All right, and so in this section, you know, we're basically kind of just focused on one thing. So we want to basically come up with a way to track human motion and track it and quantify it and measure it in a systematic way. Okay. And the way that we do this, at least in the kind of industry standard way, is to use motion capture. Is there a question? Okay. And so remember, the basic idea is that, you know, we're going to place these kind of tracking markers, these almost kind of photoreflective tracking markers on a person's body, and then as they move, we can track the positions of each of the body segments. Okay. Okay. And so eventually, you know, what you'll be able to do, and you're going to do this in the next homework, is that based on the positions of the markers, we'll be able to form a reference system or a coordinate system per body segment. Excuse me. Okay. And so visually, it's going to look something like this. And so let's say that, you know, I'm just going to focus on someone's arm for a second. Okay. Okay. And so here we have a person's arm. So we have the upper arm, the lower arm, and the hand. And so this is three different body segments. All right. And so if we just look at the 2D, you know, the 2D system, although the 2D system is you know, a little bit simplified kind of compared to what we do, but I think this is kind of easiest to see, right? For each body segment, we can attach kind of like an X and Y axis to them. Okay. And we can label each of those systems, you know, with their X, with the directions of their X and Y. Okay. So this is important because, you know, by establishing a local coordinate system in each on each body segment, we can basically look at the difference in orientation of the different coordinate axes to basically quantify, the relative motion or the relative positions of each of the body segments. Okay. Okay. And so ultimately what we want to compute are the joint angles, okay? Where the joint angles are the difference in orientation. I didn't really mention this last time, although, another thing that you can get from motion capture is the position of the centroid of each body segment. So that is also going to be important for tracking motion as well. Okay. And so that's also used, of course, right? But the tracking of the centroid is more or less straightforward. And so there's not really much to do with that. And so you basically just take the centroid of the three markers that are on there, and that gives you your centroid. Okay. But the thing that's actually harder to compute and the harder to kind of process are the joint angles. And so that's kind of what we're going to focus on the most. Okay. Okay. And so to actually process this, and so to actually process that data and get and obtain, actual angular values in terms of either radians or in terms of degrees, we have to use a mathematical tool called transformation matrices. And so that's basically where we left off last time. Okay. So transformation matrices is not a concept that's unique to biomechanics. In fact, it's used in all kinds of different methods. So I know some of you are in my finite element class 410. So we're actually just going over these, or we just finished going over these in that class. And so some of this is going to be a repeat of that. But I think where this class is going to be different is that we're actually going to take this to the third dimension as well, because 3 dimensions is kind of important for human motion. Okay. So a transformation matrix, just by itself, is a way to kind of transform the coordinates or transform the description of a point in one reference frame to another. Okay. Okay. And I want to emphasize something really about this. And so, transformation matrices does not actually move your physical object, right? It's just a different way of describing the location of that object, right? And so we do this all the time in real life too. And so, let's say let's look at the projector, right? And so if I were to describe the position of that projector relative to where I'm standing right now, I would say that projector is maybe like, I don't know, maybe like 10 feet away from me right now, right? But if I were to say, I want to track the position of that projector relative to that light right above it, right? And so the position, so relative to that light, that projector may be only, I don't know, 2 or 3 feet, maybe 2 feet below that light, okay? And so the projector is not changing position. The projector is in the exact same place, It's just that how you describe it relative to something else, that's going to change, okay? And transformation matrices are the exact same thing. So let's say that we have a single point, okay? So we'll call this a point P. And so if we were to describe the position of this point relative to some standard coordinate axes, X and Y, right? We would say that the position of that point is given by its X value. So we'll call that XP and YP, right? And so X position, XP and YP, right? That's the position of that point relative to the standard X-axis and the standard Y-axis, okay? Okay, so that's the position of the point, okay? Without moving the point, so we're gonna leave the point in the exact same place, okay? All I'm gonna do is I'm gonna shift my coordinate axes a little bit here, okay? In fact, this shifted coordinate axes, I'm gonna say is relative to the original axes, okay? But just rotated slightly, okay? And so in purple right here, I've drawn kind of a new coordinate system. We'll call it X prime and Y prime, okay? And we'll say that the rotation angle here is theta, okay? So both coordinate systems have the same origin, just one is just rotated relative to the other, right? We can again describe the position of this point relative to these axes. And so I'm actually gonna tilt my iPad to make sure I draw this correctly, okay? Okay, close enough. Okay, and so relative to that new coordinate system, we have different coordinates here, and so we have xp prime and yp prime. Okay, and so xp prime and yp prime are the positions of the point P in the new coordinate system. Okay, the point P has not moved at all, right? And so it's still in the same place. It's just how we describe its location is going to change because the coordinate axes have changed. Okay. Right, and so this is the idea of the transformation matrix, and so the word transformation is a little bit of a misnomer, just because when people think of transformation, people think of actually changing something because you're transforming something, but we're not really transforming anything. We're only really just transforming the coordinate axes. But what we're describing, the physical objects that we're describing, are still in the same place. It's just the relative position is a little bit different. Okay. Okay. But of course, if our perspective changes, if our reference frame changes, then these two quantities here, this xpyp and xp prime yp prime, these are going to have different values. And so the transformation matrix is, how do we relate these two descriptions? Okay. Okay. And so that's all we're doing is we're kind of relating kind of different definitions. Okay. Okay. Any questions on this so far? Okay, so let's actually go through the math in terms of how we can actually determine what this transformation matrix looks like. Okay. Okay, so just like the name implies, a transformation matrix is a matrix. Okay, and let's see if we can define the entries of this matrix. Okay. Okay, so there's a few ways that we can do this. This is generally my my own favorite way. Okay, and so let's take you know, the way that I like to derive this is let's describe the unit vectors in the transformed system relative to the original system. Okay. Okay, so I'm going to use the same kind of system that I have up here, right? And so in purple, the x prime and y prime, that's what I'm calling the transformed or the rotated system. And the in the black, I have the original coordinate system, which is our traditional x and y. X is purely horizontal, and y is purely vertical. Okay. Okay. And so if we were to draw a unit vector in the x prime direction, okay, it would look something like this. Okay. So we'll call that I prime. Okay. And if we were to draw a triangle, you know, it would look something like this, right? Or that angle that the vector makes the horizontal, that is the rotation angle. Okay. And then we have two sides of this triangle, which is the x and y sides of that triangle. Okay. So I prime is a unit vector in x prime direction. Okay. And so let's compute the lengths of the two other sides, and so x and y. Okay? Because by the fact that we know I prime is a unit vector, we know I prime has a length of 1. So the length of this vector is 1. Okay. So we know the length of the hypotenuse of this vector. Okay. So let's use trigonometry here to compute the values for x and y. Okay. So x here is going to be the length of the hypotenuse, I prime, multiplied by cosine of theta. Okay. And y here is going to be I prime magnitude multiplied by sine theta. Making use of SOHCAHTOA, right? So you know, cosine is the adjacent divided by the hypotenuse, and sine is the opposite side divided by the hypotenuse. Okay, and I just rearrange things a little bit. Okay. And so we know, just because I prime is a unit vector, we know those both have magnitude of 1. Okay. And if we use vector addition here, we can say that I prime, okay, because x here is a unit vector in the original x direction, y here is a unit vector in the original y direction. So what we can say is that I prime is equal to cosine of theta times I plus sine of theta times j. Okay. I is a unit vector in the x direction, and j is a unit vector in the y direction. Okay. All right, so this equation here is going to form one row of our transformation, one row of our transformation matrix. Okay. All right. Any questions on how we obtain this this equation right here? Okay. All right. So let's do the same thing for J prime. Okay. All right. So the J prime in this configuration right here is kind of pointing up and to the left, and so let's go ahead and draw that. Okay. So this is our J prime vector. Okay. And same thing, I'm going to make a right triangle with it by drawing a vertical line and a horizontal line. Okay. And just like before, I'm going to draw X and Y. Okay. All right. So one thing that's a little bit different here is that you can see that our X vector, our horizontal vector here, is actually pointing to the left. And so this is actually going to be a negative coordinate. Okay. And because it's pointing to the left, we say it's pointing in the negative X direction, the negative direction of our original coordinate system. Okay. Okay, so once again, let's use trigonometry here. And so we have X is equal to minus magnitude of J prime sine theta. Okay. And Y here is going to be positive magnitude of J prime cosine theta. Okay. Once again, we're going to take advantage of the fact that J prime here has a magnitude of 1. Okay. And so just like before, we can say J prime is equal to minus sine I plus cosine of theta J. Okay, so let's put these two equations together. Okay, and what you'll see is that we'll be able to form a matrix system from here. Okay, all right, so we have, first thing we had was that I prime is equal to cosine theta times I. So where I and J are the worst letters to use for this, so I get them confused all the time. Okay, cosine of theta times I times sine of theta times J. Okay, and then we have J prime is equal to minus sine theta times I plus cosine theta times J. Okay, so we have a two equation system, right? But if you'll notice, both the top and bottom equations have both I and J. And in fact, these are linear equations in I and J as well, right? And so we can kind of separate this out into a matrix system. Okay. Okay. And so we make a matrix system that looks like this. Okay. I took advantage of the fact that these are just simply linear equations, and so I factored out I and J from both of those equations and put it in a matrix here. Okay. Right. This matrix that comes out of here, this is a transformation matrix. And that's exactly the transformation matrix that we're looking for in this, in this part here. Okay. All right. So the way you can use this, and so the way that this system is written here is that this will basically let you convert any coordinate in the original system to the transform system. Okay. And so the way this works is that, instead of I and j on the right-hand side, you would plug in the coordinates of the original point in the original system, okay? And then you just multiply it by this matrix, right? And then after multiplying by this matrix, you're again going to get a vector, a 2x1 vector, but that vector is going to be of the new coordinates, okay? That remember when we're transforming, the point physically is staying in the same place. It's just that we're changing our description and how we describe its location. Okay, so let's do a very quick example to kind of show how this works. Okay, and so let's say that our point P has coordinates of 3, 2. And so if our rotated system was rotated 30 degrees counterclockwise, we want to compute its coordinates in the rotated system. Okay. All right, so visually it looks like this, right? And so we have our normal system. Okay, 3, 2, we'll say is like around there. Okay. Okay. And so if we were to rotate the system 30 degrees, this one's kind of whack right here. You want to find out, what are the coordinates of this point in that rotated system, right? So, what are its x prime location and x or y prime location? Okay. All right. So that's visually kind of what we're doing. So let's compute our transformation matrix. And so our transformation matrix, let me call it, I'll call it R, okay? R for rotation, okay? Okay, so our theta here is 30 degrees, so we're gonna have cosine of 30, sine of 30, minus sine of 30, and cosine of 30, okay? All right, and so we just compute those, and so we get root 3 over 2, 1/2, minus 1/2, root 3 over 2. Okay. And then to get the I prime or the x prime, y prime, okay? Essentially, that's kind of what we want. We're going to multiply this by the x and y coordinates in the original system, which are just 3, 2. Okay. So we have to perform this matrix vector multiplication of our matrix multiplied by the vector 3, 2. Okay. All right, so I'll let you kind of verify this, and so you can perform the matrix vector multiplication. But if you do that, looks like I was going to say use a calculator, but it looks like I did not use a calculator. So I computed this by hand, and I was too lazy to put decimals here. Okay. that is the x prime and y prime coordinates. Okay, so this first entry here, this is the x prime, and the second entry will be y prime here. Okay. So that's just kind of a quick example of how to use these transformation matrices. Okay. Remember, it's only a change in the description, right? And so it's the points themselves aren't moving. It's just that how we describe the locations of those points are different. Which I think, the first time you're kind of introduced to this, it's a little bit of a shift in paradigm, because x and y coordinates, I think for the most part, for most of your classes, have always been kind of the horizontal and vertical axes, right? And everything has always been described relative to those kind of axes, right? But you could just as easily kind of change the position of those axes based on either rotation or transform or translation. We'll talk about translation a bit later, okay? And that's going to change how we describe the location of points in space, okay? But remember, the points themselves aren't moving. It's just how we describe those points are changing. Okay, any questions on this example here? Okay. All right, and so before we move on to 3D, let me talk about kind of a really nice property of the transformation matrices. Okay. Okay. Because right now the transformation matrix, as we're describing it, basically transform the coordinates from the original coordinate system to the rotation. Okay. You can reverse that direction, right? And so let's say that you have coordinates in the transform system and you want to transform it back into the original system. Okay. You can reverse a transformation matrix. Unfortunately, you just can't use the same one as it is. Okay. You have to kind of work on it a little bit. And the way that you reverse it is by simply taking the transpose. So let me kind of show you what that means. Okay, so our transformation matrix, as it is right now, is cosine theta, sine theta, minus sine theta, cosine theta. Okay. So this matrix here transforms from the original system to the transform system. If we were to transpose this, right? And so transposing basically means that you take the rows and you write it into the columns, okay? So we do RT, then we'd have cosine theta minus sine theta, cosine theta. Okay. All it really changes here is just the position of the negative. So instead of the negative being the bottom left, it's now in the top right. Okay. Okay. And so basically the way to use this transform matrix would be like the following. So it would be like I, J, maybe I should say XY, kind of be bit more general. Okay. Where XY would be coordinates in the original coordinate system. Okay. And you have cosine theta minus sine theta, cosine theta. Okay. And the thing that you would multiply by this matrix would be the coordinates in that rotated system. Okay, so this would be x prime, y prime. Okay. Right, so notice the positions of these two vectors are swapped. So when we're using the original matrix here, we had x prime, y prime to the left of the equal sign, okay? But now that we took the transpose, the x prime, y prime are appearing on the right side of the equation, which is post-multiplying this matrix here, okay? Right, so this is going to be important because, as we go to 3D, what you're going to see is that, we're going to need to reverse the directions quite a bit. And then when we relate this back to motion capture, this property is going to be useful as well. Okay. All right. Any questions on this? Okay. Okay. So let's go to 3D. Okay. So the good news about 3D transformation matrices is that we can obtain them by doing multiple 2D transformations. Okay. Because in 2D, there's really only one rotation we can make, right? But in 3D, there are basically three directions we can rotate. Okay. Right, and so tracking angles in 3 dimensions is a lot more complicated than 2 dimensions because we have so many different angles to consider. Okay, but the good news is that these 3 rotations can be considered as 3 2-dimensional rotations. Okay. Okay. And in fact, you can think of it as performing these 3 rotations sequentially, right? So we're going to rotate in one plane, then another plane, then in the third plane. Okay. Okay, and so to illustrate this, we're going to use an analogy. I think this one's a pretty good analogy in the space of analogies. And so we're going to pretend that we're kind of sitting on a plane and it's about to take off, right? So you're kind of on the target. Okay. And so as the plane takes off, it's going to go through a series of rotations about several different axes, right? And we can track those transformations using our 2D transformation matrix. Okay. And if you're familiar with aeronautic terminology, we're basically going to be tracking the yaw, the pitch, and the roll. But if you haven't heard those terms, then don't worry about it. It's not important for this class, but it's just some people have heard of it, so I thought I'd kind of make that connection. Okay. Okay, so let me go ahead and draw the picture here. Okay. So let's say that we have an airplane. I'm going to do my best here to draw an airplane. I swear, I think I spent 20 minutes drawing this in the notes, but up here I only have about 20 seconds, and so. Okay. I don't know what's going on with the tail. Don't worry about it. Okay. So an airplane is nice because the kind of the geometry of the airplane aligns very well with kind of a standard X, Y, Z coordinate system. Okay. And in fact, we're going to define our original kind of our unrotated system relative to this orientation of the plane right here. Okay. Okay. So we're going to assume the X direction kind of goes right down the length of the plane. The Y direction is going to go down the wings. And the Z direction is going to point, upwards and downwards. And so, we can either choose to have it point up or down, but based on the positions of these X and Y directions, and based on the right-hand rule, the positive Z direction is actually going to be pointing down towards the ground. Okay. Okay. So right now the plane is on the ground. So, we're perfectly kind of horizontal with the ground. Okay. As the plane starts to take off, we're going to perform rotations around each of these axes. Okay. And let me give each of them a name. Okay. Okay. So let's call the rotation about the Z direction. We'll call that theta. Okay. So that's the yaw. Okay. Then rotation is about the y-axis. So that's the rotation that's going to point the nose up or down. We'll call this angle phi. Okay. And then rotation is about the x-axis here. That's our final direction here. Okay. Eventually, that's going to be used to turn the plane in 3 dimensions. We'll call that psi. Okay. Okay. And so we're going to use transformation matrices with each of these angles here, and then combine them all into one later. Okay. But let me just make this note first. And so in this configuration, with the plane on the ground and it hasn't started moving yet at all, just a little terminology, we're going to call this the lab frame. Okay. And so that's kind of referencing the fact that, whenever you're doing any kind of experiments, either motion capture or biological experiments, we kind of always assume that whatever lab that we're standing in, that we're physically in, taking the measurements in, that's kind of our fixed stationary frame that we measure everything relative to. Okay. Okay. So you can think of this as kind of standard X, Y, Z. Okay, so you're gonna see me use the term lab frame a couple times. So you just want to make sure that you kind of know what that means. Okay. So let's go through our rotations here. Okay, and so we're going to go through each of the yaw, pitch, and roll rotations, and see what they mathematically look like using transformation matrices. Okay. Okay. So let's go through the first rotation first. Okay. right? So the first rotation is going to be yaw rotation. That's going to be a rotation around the z axis. Okay. Physically, what's happening is that the plane is on the tarmac. It's kind of taxiing, trying to get to the takeoff location. Okay. And so to get there, sometimes the plane has to kind of make a turn on the ground. Okay. And so this rotation is going to be theta in the diagram that we have above. Okay. So let me draw the transformation matrix for this. Okay. Okay. And so normally our transformation matrix is only 2 by 2, but since we're in 3-dimensional space here, we have to kind of expand that. Okay. And so the way we do that is we kind of just expand this matrix out by one space. Okay. And so since we're rotating about the z-axis, okay, that means the third column and the third row are going to be special here. Okay. And so in the third column, we're going to have 0, 0, 1. Okay. And then our last row is like that as well. Because we're not changing anything relative to the z-axis. And so our z, if we were to measure, the xy position here, the z direction wouldn't change as a result of this rotation. Okay. And that's what this kind of represents. All right, so we're just going to insert our 2 by 2 transformation matrix in the slots that are remaining. Okay, and so we have cosine theta, sine theta, minus sine theta, and then sine theta, cosine theta on the second row. Okay. And so of course here, what you're seeing is that I'm using kind of the transposed version of this. Okay. Where the negative sign is in the top right. Okay. And so of course this is a transformation from it's from the rotated system back to the original. Okay. Okay, so we're gonna have a few different transformation matrices here. So let's make sure we kind of label that here. So let's just not call this R. Let me add some superscripts and subscripts here to kind of indicate that. Okay. Okay. And so remember, our original orientation here was the lab configuration, right? And so actually, let me kind of label that. And so instead of the original system, let's call this the lab system. Okay, and so the standard that I'm going to use here for the transformation matrices is that whatever's in the top left, that's what we're transforming to. Okay, so that's our destination, and then in the bottom right here, that's going to be our original, or that's going to be what we're transforming from. Okay, and so in this case, after the first rotation, we're going to end up in configuration 1. Okay, and so this transformation matrix transforms from configuration 1 back to the lab configuration. And so call this lab R1. Any questions on how we obtain this this matrix here? Okay. Okay. And so before I move on, you know, I want to make a couple comments here about kind of the position of this negative. Okay. Because the position of that negative is actually quite important. Okay. And so, you know, in this case, you know, we put the negative in kind of the top right here. Okay. And so let me give you another interpretation of the transformation matrix. So, you know, the transformation matrix is, you know, can be interpreted in lots of different ways. Okay. Okay. And so another way to kind of interpret the transformation matrix is that, you know, well, and we kind of discussed this before too, but, you know, I think it's worth repeating. Okay. The columns of the transformation matrix are the coordinates of the unit vectors in the new frame. Okay. When expressed relative to the old frame. Okay. So you can use this definition here to kind of you know, determine where that negative is going to be. Okay. And so the cosine terms are always going to be the same spot. So we're going to have a cosine theta on the diagonals all the time. Okay. And you're going to have a sine theta on the off diagonals all the time as well. Okay. The only question is, you know, where do you put the negative sign? Okay. And so for this particular case, you know, we're performing a counterclockwise rotation, you know, about the z-axis, right? So let me kind of draw what this looks like. Okay. Okay. And so in our original lab frame, you know, we have the x lab axis and the y lab axis, right? And then after we perform the rotation, we're going to have x1 and y1. Okay. Where this angle is theta, this angle is theta here. Okay. Okay. And so let's look at this definition again, right? And so the columns of the transformation matrix are the coordinates of the unit vectors of the new frame, right? And so the unit vectors of the new frame are these ones, right? And so the new frame is x1, y1. And so if we draw a unit vector in this direction, okay, and a unit vector in this direction, right? Okay. So those are the unit vectors in the new x and the new y directions. Okay. What we're representing them as in the transformation matrix are, you know, we're representing these coordinates relative to the old frame, right? So, you know, we have this vector right here, okay, expressed relative to x lab and y lab, right? Okay, so let's look at this. Let's look at this vector right here, right? We don't have to compute its exact coordinates, but we can see that, you know, this point right here for the first unit vector is in the positive x lab direction and the positive y lab direction. Okay. Right. Whereas this unit vector right here, right, it's in the positive y lab direction, right? It's above the origin here, okay? And so its y lab coordinate is positive, but it's to the left X lab, right? And so this point right here is negative X lab and positive Y lab. Okay. All right, and so this negative right here tells you that's where that negative is going to be, right? And so we look back at the transformation matrix that we derived here, okay? And we look at the columns, okay? And so that first column is the position of the x1 vector, right? And so both of those are positive, so the cosine theta, sine theta, right? That second column is the position of the y prime vector, right? So remember, for the y prime, we had negative x lab, and so that's that negative sine theta, and y lab is positive, so it's positive cosine theta. Okay, and so if you're ever unsure, so if you're making these transformation matrices and you're kind of unsure kind of where that negative is, draw it out. And so and that's kind of the answer to a lot of problems in biomechanics is draw it out, kind of visualize, see what's going on, and then kind of make your decision based on that. Okay, because and once you kind of get good at this, you can kind of just talk through it and kind of visualize it in your head. But it's kind of a lot of geometry to kind of keep track of it. So I do this all the time. I always have to kind of draw things out just to kind of make sure I'm putting things in the right place and making the signs all correct. Okay. Any questions on this so far? Okay. So that's one transformation, right? And so we've kind of, we're on the tarmac and we've kind of rotated, heading towards the runway. Okay. And so as the plane takes off, we need to do 2 more rotations. All right, so the first, well, let me call this 2 and 3, okay? Because technically this is the second and third rotations, okay? And so the second rotation, let's say that we're on the runway and the plane starts speeding up, and then we start to point the nose up as we take off, okay? Okay, and so taking off is going to involve pointing the nose upwards, and so this is going to be a rotation about the y-axis. Okay, so let's go back here. What you'll notice is that relative to this system here, we're kind of rotating in the theta direction. Okay. Right. So this is or not theta, phi direction. Okay. All right, and then after we've taken off, and so the plane is in the air, and then in order to kind of turn and get it towards its flight path, we have to kind of turn, right? And so a turn in the air is going to be a rotation about the x-axis. Okay. And then in our figure there, it's going to be the psi angle. Okay. So just for the sake of time, I'm just going to kind of write out what these transformation matrices look like. Okay. We're going to use the same convention that we used for the first rotation matrix. So these are going to be 3 by 3. One of the rows and one of the columns are going to be canceled out because we're only rotating in one direction at a time. Okay. And the location of the negative is going to correspond to the standard that we just drew here. Okay, so first thing we're going to do is going to be the rotation matrix for step 2 right here. Okay, so this is takeoff. And so this can be the transformation matrix between state 1 and state 2. Okay, the y-axis corresponds to the second row and second column. So actually, this is the one that kind of looks the strangest because we have a 0 in the second row and second column with a 1 on the main diagonal. Okay. we have cosine phi in the top left and bottom right, and we have sine phi in the top right and bottom left. Okay. Notice the position of the negative here has changed, and if you want confirmation of that, you can kind of draw it out just like we did before. Okay, so the negative here is actually in the bottom left. So that's going to be the transformation matrix for step 2. And then for step 3, okay. So this is going to be the transformation matrix between step 2 and step 3. Okay. It's going to be a rotation about the x-axis, and so we're going to have 1, 0, 0, 0, 0. Okay. And then cosine of psi minus sine of psi sine of psi and cosine of psi. My psi's are getting uglier and uglier as the day progresses. Those are psi's, those aren't 4s. Okay, so those are 3 transformation matrices, and so we've done kind of 3 rotations about 3 coordinate axes, and each of those individual rotations can be described using these transformation matrices. Okay. All right. Any questions on these so far? Okay. So this is good, right? And so we have 3 separate transformation matrices, but ideally, we'd want to have one transformation matrix for the entire transformation. Okay. So technically, we can use these 3 transformation matrices, and so if we wanted to, we could take a coordinate, or the location of a point and just multiply by each of these 3 matrices, in succession, right? And so we multiply by R map 1, R1 2, R2 3, right? So that's possible, but it would be nice to have just one matrix and capture the whole thing. Okay. All right, so to do this, it's relatively simple, or at least in theory, it's simple. Algebraically, it's not simple. In fact, it's something that we're most definitely going to skip. Okay. Okay. But to combine sequential transformations, all you have to do is just multiply the transformation matrices together in the right order. Okay. And so actually the notation that we've been using today is going to be helpful because it's going to let us cancel some things out. Okay. Okay, so let me write out the 3 transformation matrices, at least their symbols. Okay. So the first transformation matrix that we talked about was the transformation between for the yaw rotation, right? So that's going to be lab R1, right? So the transformation between after the yaw rotation back to the lab frame. Okay. Then we did a pitch rotation, so that's 1 R2. Okay. And then we did a roll rotation, so that's going to be 2 R3. Okay. if you notice here that, when I multiply these transformation matrices together, the inner dimensions should be the same. Okay. So you can see that, we're multiplying lab R1 to 1 R2. So these two have to match. Same thing here. Okay. Okay. Right. So that's really important. And in fact, we're going to make use of this property a lot once we kind of relate it back to motion capture. Okay. Because what's going to happen is that if you have these inner dimensions matching, you can essentially kind of cancel them out. Okay. And so what you're going to be left with in the end is just one transformation matrix that transforms between the two things that are remaining. Okay. And so on the left-hand side, we have lab. And on the right-hand side, we have 3. Okay. Orientation 3 being the final orientation after we perform those 3 rotations, right? The yaw, the pitch, and the roll rotation. Okay, and so that one matrix is going to capture all 3 steps of that transformation. Okay, and so we have 3 3x3 matrices, and so we can multiply together. We can perform all of the matrix algebra that's involved in this, right? And if I hated you guys, we would actually do it in class, but I don't. I like you guys, and so I'm just going to give you the answer. Okay. And so after lots of painful algebra, we get the following result. Okay, so it's again going to be a 3x3 matrix here, but the entries are going to be a lot more complicated than they were previously. Okay, so in the top left here, we have cosine of phi, cosine of theta. Okay. Then we have sine psi, sine phi, cosine theta, minus cosine of psi, sine of theta. Okay, so that's the second entry in the first row. And then the third entry in the first row is cosine psi, sine phi, cosine theta, plus sine psi, sine theta. Okay. So that's the first row. Okay. And in fact, let me kind of draw dotted lines here to kind of indicate the separations between the entries. Okay. Draw a dotted line there as well. Okay. Okay, second row. So second row, we start with cosine phi, sine theta. Okay. Next entry here, we have sine phi, or sine psi, excuse me, then a sine phi, and sine theta, plus cosine psi, cosine theta. Okay. Then we have cosine psi, sine phi, sine theta. Okay. Minus sine psi, cosine theta. Okay. Okay. And then in the last row, thankfully is a lot simpler here. We have minus sine phi, sine psi, cosine phi. And then in the bottom right, we have cosine theta, cosine phi. Okay. All right, and so this is kind of the the ending point for today. Let me, we have about 1 more minute. So, basically what we're going to be able to do is that, given mocap data, we're going to be able to compute a matrix like this. Okay. And then the way to obtain the joint angles is basically to derive them from this matrix. Okay. And so even though, today we've been calling these angles kind of the yaw, the pitch, and the roll, right? Another kind of interpretation of these, if these were to kind of describe human movement, is that these angles, theta and phi and psi, these are kind of the joint angles that we're looking for. Okay. And once we have kind of numerical values for this matrix, we can use the formulas for each of these entries here to determine, what psi, phi, and theta are. Okay. In particular, the last row in the matrix is probably the easiest to use, just because the expressions for that row are kind of the simplest. Okay. You can use the entry in the bottom left to solve for phi. Explicitly, and then once you have phi, you can use the next one to solve for psi, and the last one to solve for theta. Okay. All right. Any questions on this before we wrap it up today? Okay. All right. So next time we'll do an example. Maybe I think I'll probably preview one of the homework problems for you, just because the homework is a little bit different than kind of the examples that we're doing. So let's plan for that next time. Oh, and to do that, I need to post the homework. So. I'll post the next homework assignment before the next class. We'll kind of just review kind of briefly kind of what I'm looking for those problems. And we'll kind of wrap up this section on human motion kinematics. Okay. All right, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys on Wednesday.
So, my registration date is tomorrow, but I was wondering do you know if they're going to open any more 476B sections? Because there's like only 3 or 3 or 4.
So I think it's possible. I need to talk to the department chair.
Okay.
So I know every year, for the labs, we offer enough sections so that everyone who needs to take it will be able to take it. And that's a situation we kind of monitor in real time.
Okay.
And so in the past, what we've done is we've added new sections just as the demand kind of steps up.
Okay.
But I know that a situation that's happening that's unique to next semester is that we're pretty short staffed next semester.
Okay.
And so I know the department chair, he's trying to kind of scramble and find instructors specifically for the lab courses.
Okay.
And so the only ones that's there right now, maybe the only ones that we have kind of a commitment from an instructor for, so that may be why the amount of sections is low.
Okay.
And so if there's only 3 sections, I expect more to be added.
Okay.
But I'd have to talk to the department chair just to make sure.
Okay, because it just conflicts with like another class I want to take, which
Yeah.
is like tough because all of the they're all waitlisted too.
Yeah.
But okay. But do you think if I can't take that class, do you think it's like difficult to take both during the summer?
No.
A and B?
Yeah, people do all the time, and we schedule it so that both are on the same days. I think it'll be tough just because it's a lot of work for the lab reports to kind of be on top of both at the same time. But we have people take both over some.
Okay.
So, yeah.
Okay. Thank you.
Yeah. Hey.
So who's teaching the finite elemental analysis class for this for the 400 level, right?
Yes.
You know if you're going to be teaching the 500 level next semester?
Yes.
Okay.
That is the plan.
Sweet. So I'm a graduate student, which means I can kind of I don't know if I'm allowed to just take it. I'm going to
Yeah, you are.
about that.
Yeah.
Okay. I want to, and I am gonna try to like watch your like lecture series. 'Cause
Okay.
I don't have like, I mean, I have a math background, but I
Yeah.
don't have like elemental analysis background.
That's okay. Yeah, no,
So-
I teach the class. I mean, I mean, it'd be great if you did,
Mhm.
but I teach the class kind of expecting this is kind of everyone's first exposure to finite elements. So
Okay,
it's,
so,
it's not required.
Yeah. so like if I make a bad plan and I don't end up getting up to it, then like I'll be okay still.
Yeah,
Okay,
you'll be totally fine.
awesome. And then you're also teaching the cardiovascular one,
Yes.
the bio one.
Yep.
Yeah, that one sounds fun.
Yeah. A little bit of a follow-up to this class, but much more fluid mechanics. Because this one we're doing more like kind of kinematics, dynamics,
Yeah,
but cardiovascular is more fluid. It's just
Yeah.
natural.
I'm kind of interested in that because like UCR, I like live right next to UCR, and they got like biomechanical program, and the like teachers doing that is like they're focused on like heart stuff.
Awesome.
So I'm
Very
like,
cool.
ooh, I wonder if I could like try to get into that one, as like a what's it, not degree, it's like a PhD.
Yeah.
So that'd be fun. Do you think you're gonna offer those like online, like you did these?
Yeah.
Yeah.
My lecture plan is, at least for the foreseeable future, is going to be just like this. So
Okay.
stream on Zoom, but I'll be here in person. But you know, as always, the exams will be in person.
Yeah.
And what's going to be unique about 442 is that the final project is going to be different. So I'm going to have you guys use research software to actually build like a CAD model of someone's blood vessels and run a simulation. So there's going to be some kind of more hands-on activities for that. And so for those, I do recommend that you join in person too for that. But for the most part, the lectures will be virtual.
Okay. You also mentioned you were working on some CAD, not CAD software, but yeah, computer aided design for like biomechanics, right?
Yeah.
Like at some point earlier. What was the name of that one?
So that one I don't work on, but I've used it before. So the one that's paired with this class is called OpenSim.
OpenSim.
Yeah.
Okay.
So that one's dedicated to kind of human movement, muscle. So like very, I mean,
Okay,
the
so it's
textbook we
what
use
we're
is
doing.
written by the guy who wrote the program too. So
Okay, so like
so
that'd be right there.
exactly, yeah. And so they have a lot of so if you just search up OpenSim, then you'll find that software. It's very good. It's one of the better ones.
Okay.
Yeah.
OpenSim. Yeah. I'll see if we can like we find we could integrate it somehow for like our project, but
Yeah, no, that'd be great.
meeting students who might be interested.
Yeah. In fact, you know, and unfortunately, I don't think we're gonna get there just because we're a little bit behind from where I wanted to be. It's interesting because I didn't take into account we had that 1 3-day weekend early in the semester where we missed a lecture, and that threw everything on. So this whole semester I've been trying to catch up. So I don't think we're gonna get to OpenSim in the class itself.
Okay.
But if you want to look into it for your project, I think that would be fantastic actually. So,
Okay. Awesome. Thank you.
Mhm.
All right. Have a good one.
thanks. Hey guys,
They didn't add your class yet to the option, right?
for what?
For cardiovascular.
It counts as a technical elective. It's just because it's a special course that it's
It's not in the. It's not in the catalog. yet.
oh, it's not? Oh, it should be.
When you search it up,
Oh, really? Let me see.
the only tech electives that are available right now